I would like to present our research work titled "The Improvement Embankment Seismic Resistance by Selecting Suitable Geogrid Location in the Subsoil." The work has been made based on numerical simulation and statistical modeling. Outline of present study content of 5-part highlights: introduction, method for simulation, result for engineering decision making, and at the final conclusion. Highlight: geogrid location has been studied, nonlinear displacement and nonlinear deformation of embankment subsoil have been studied, failure mode of model is studied. Introduction. The mechanical property of soil support the load serviceability for soil foundation. When suitable mechanical property are not available in the construction site, we can use mixing soil method, but this method has limitation. In this case, we need to use reinforcing soil technique. Vertical and horizontal displacement of the model, strain energy density and magnitude, seismic wave characteristic receive significant attention. In the literature, find the applying multi-directional seismic load on the model shown better result, and it need to apply three-directional seismic load on the model. In this investigation, two concepts need to understand and simulate. First, steel, and second, soil. When we are applying seismic on the model, the steel has only movement, but soil has movement as well as deformation, displacement, and maybe crack extension. Here, we need to identify best location of geogrid to estimate embankment, subsoil displacement, and deformation to improve seismic stability of the model. The main objective of here is to identify location for installing the geogrid and nonlinear deformation and displacement and prediction failure mode of the method for simulation. Method of simulation here is numerical simulation based on FEM software, Abacus, commercial software. Steel, we use steel for assembly geogrid in the FEM software environment, and we applied a seismic load on the model, and geogrid soil interaction has been introduced to the software, and based on these results we have from the numerical simulation statistical technique applied for the interpretation of the result. Table here is presented mechanical property for the soil and the steel. We have one soil and one steel. The seismic load in multi-directional are presented here in X, Y, and Z direction, and characteristic of acceleration at all three directions, and it's applied to the model. Three model we have here. The first model is without any geogrid, is the first model of here. We don't have geogrid, and in second model the geogrid is installed in subsoil, and center of the geogrid is under toe of embankment. And in the third model, we have the geogrid in subsoil and is not located under the embankment. All stage of the numerical simulation here is need for analysis. And here we have dimension of 3 model, and but thickness is not shown here. Thickness for all model is 40 meter. And okay, what we have here, after applying the seismic load on the model and the result of the numerical simulation are showing here. What we have here, we have the 3 model 1, 2, and 3. What can understand here, model 1 is collapse with lower displacement, what is here, and the model 2 is showing higher resistance, and higher resistance we can find in the model 2. The result for the engineering decision making. What we want to know here in the best location. For finding the best location, we need to know what is happening after the seismic load. The path loading change with a change of geogrid location in whole stage of the numerical simulation are showing in this picture. And model 1 is collapse with lower displacement and also non-linear displacement, and deformation are changed with respect to the geogrid location. Install geogrid in best location improve the flexibility of the model, and embankment and displacement collapse with higher displacement, and means allowable displacement has direct relationship with the location of the geogrid. Higher tensile strength of the model lead to delay in the model collapse. Install geogrid at the beneath of the toe of embankment make subsoil and embankment more stable. Vibration mechanism change of the vibration mechanism change at each model. Vibration of mechanism is related to the possibility of the damage may happen on the model. And nonlinear displacement with the time is need to analyze based on the prediction of deformation and displacement. What we have here, we use the statistical modeling for prediction of the result. If we come to model 2, in this model 2, what we have higher expected normal value compared to the model 1 and 2 when the nonlinear displacement are investigating in all 3. Conclusion. The installation of geogrid in suitable location of subsoil change the vibration mechanism, deformation, and displacement pattern of model. In model 1, the embankment is collapsed with lower displacement compared to the model 2 and 3. The flexibility and seismic resistance of the subsoil model are related to the soil geogrid interaction. For technical application in the estimation of seismic nonlinear displacement of the embankment subsoil model, the exact location and shape of geogrid need to be designed. Future research need to evaluate a cost-effective technique for geogrid design, and in addition, geogrid soil interaction require investigating in detail. Thank you so much.